Okay, our plan for today. We are going to talk about recursion, which we didn't get to last week, which is totally, that was part of our plan. Actually, it's not to get here. Uh-oh. It's not me, is it?
No, it's not me, sir.
After we talk about recursion, we're going to talk a little bit about errors, troubleshooting, if you will, in MATLAB land, now that we're getting into more complicated stuff. Then we'll talk about dynamical systems. We'll do two examples. We'll do one, a cantilevered beam. And then we'll do a free fall example. Both of those are really pretty cool, I think. And then we'll talk through exam-free practice problems. And I definitely want to spend some time together talking about them. They are, I don't feel like there's any new stuff being asked in them, but they're combining a lot of stuff we've done together. And in that way, it may feel new. And I want to make sure we all talk about it together. Okay? Yeah, so let's keep track of time, how we're going. If we get to somewhere around here, we don't have enough time, we might jump to this. Okay? But this I want to do at our computers, so we can tool around. You guys know the exam 3 is next week, right?
Yeah.
Awesome. All right, so if I write there, you can't see it, huh? I'll just pretend I have only one marker board. So what is recursion? Okay. We can finally introduce recursion because we have seen functions. Recursion is basically a function that calls itself. At a very basic level, it's a function calling itself. So if this block represents a function, okay, a MATLAB function, and somewhere in here, let's call this function to do. Okay. And then somewhere in here, I basically say execute function to do. That is going to start this function. Can you imagine that we have here a loop in a way? And we have a loop that theoretically could never stop if we don't construct this correctly. So part of recursion is exactly about getting to a repetition. But recursion only accommodates certain types of algorithms repeated. And we'll start to see what those look like in a second. Okay. So, like with all repetition, there is this consideration that you might keep going on to infinity. Recursion, kind of at its core, is an indefinite sort of thing. There is no way to actually define very explicitly the number of iterations. Right? I mean, there is in a not very clear way. So one thing that we didn't talk about this year, where we had talked about in years past, is this concept of the computer memory and how programs use the computer memory. So I'm going to try to do this without thinking about computer memory too much and explain the recursion. And if we have to go there, I'll try to explain as much as I can. So, if I have a definition for the function over here, and I run it, I'm basically creating what we call an instance of that function. Okay? So here's the function definition, it's a .m file set. If I call it, remember that's a term for saying run the function. If I call this function, it creates a unique instance of it. And if you remember, everything inside of that instance, the variables and all that stuff, are scoped only to that function, right? So I have an instance now here, and there's some stuff in here, and it's scoped to that. If this function is recursive, it's going to call itself. So somewhere in here, it says call itself. And what that's going to do is actually create a new instance. The original instance is still there. By calling itself from inside of here, it creates a second instance. Okay. This second instance has its own variable space, has its own scope. It's going to get some parameters from here. So there's some parameters coming down in. We'll delineate, we'll show that with the blue. Arguments, parameters, whatever you like. Okay. And of course, since it's called itself, you see that it has a call of itself again. So this instance is going to do what? Call it again. And so you can easily see how this might go on forever, right? So now we have our third instance. This third instance also got some arguments. It got its arguments from the second instance. Cool. Now we haven't gotten there yet, but let's just assume there's some way for me to stop this whole thing. Okay? So somehow in my code, I'm super smart, just like you guys. Somehow in my code, I say stop. Effectively saying don't create yet another instance. Okay? What happens at that point is this function finishes, and most of our functions return something. They don't have to, but in recursion they have to. We're going to return something to here. When this function is done, because it's that special function that had that stop, I return something, it gets returned to the second instance. What do you think happens to this third instance of the function? Done, disappears. All right. After the call, maybe I do something in here, that gets finished. Guess what happens here? This is done. It's going to return this stuff over here. What happens to my second instance? Completely goes away. Yeah? Good. You guys caught on real quick. And then this might have some stuff to finish up. It's done. What happens? It returns that one value back to wherever I called from, right? And this goes away. And unless I did some crazy variable saving, all the work, all the variables that existed while this whole repetition, this recursive repetition was occurring, they're all gone. And the only thing I get back is that one value I return. Any questions on sort of that general sort of concept so far? So the canonical, or most like classic example of recursion is the factorial. Okay? You'll see the factorial. We'll go back over here. Okay. Great example for recursion. Okay. So what does factorial look like? What's the math for factorial look like? Let's do 5 factorial, right? Just refresh our memory. What does it look like?
5 times 4 is 4.
Like so?
Yeah.
Yeah? Okay, good. So if you notice something where there's a pattern, and you can actually retranslate this into something different, could you, for example, define factorial in some sort of way as using the factorial definition in itself? This is that recursive part. Like, so if I can change this and define it as the factorial equals something something factorial. That's the mathematical way of expressing the recursion. Then I can do it in code. Okay? And what does that look like? So, well, if I ask you to break this part up and this part up, can you express this as a factorial of something? 4 factorial. So you could say that 5 factorial is equal to 5 multiplied by 4 factorial.
Oh, yeah.
Right? Business. That wasn't on tape, was it?
I think it was. So.
Hi, Alex. So this is what I meant by, could you take this definition here and say the way to determine that is some math times plus minus whatever, using that same definition again, but approaching closer to your finishing result, right? If this was 5 factorial here, which is not, but like assume there was a world where this value wasn't changing, you weren't getting closer to your final result. But here you are, you know, and then this, if you want to sort of keep the same pattern, this 4 factorial, how would I represent that? Keeping the same pattern over here. Right? Exactly. And this, same thing. So here, sort of mathematically, or in equation form, you can see how this equation can be converted into a recursive algorithm. So if I want to generalize this in using only symbols, let's use n. What might it look like?
N times n minus 1 factorial.
Yeah. You want to see that? And so once you can get to this sort of algebraic version or neutral version, whatever you want to call it, you can look at this and go, huh, that is my recursive function definition in equation form. And now it's just a matter of writing the function to do it. Let's pause there for a moment. How do we feel about this? Straightforward enough, right? Okay. This works great for a series. This works great for geometric progressions, Fibonacci sequences, all those kind of things. Those are the classic problems for recursion. Now, if you go online and you look for, you know, like, why should I do recursion? Most of the time, these simple examples, they're really used to demonstrate where recursion is, how recursion works, isn't it? They're not necessarily like implementing this in a recursive as a recursive function actually is probably slower than using MATLAB's built-in, or even just using a float. That's not the point here. The point here is to just sort of demonstrate this. If you start doing sorting and like these things that are called binary trees or graphs, where you want to, where you actually have this ability to kind of go through your data down and kind of pop back up, recursion can actually be a faster way to recursion. That's like advanced stuff. So just know that recursion can actually be very powerful and much faster in certain algorithms, but this stuff it doesn't necessarily. This is the best way to learn it. Okay, cool. So let's see. Let's write what it looks like. I want to do it on the board before we do it in MATLAB, okay? So, am I going to write a script or a function? Function. All right, what should we call it?
Recursion?
Well, what does a recursion do? In this case.
Incur upon itself?
Well, in this case, this specific recursion example is going to do
Multiply?
factorial. So let's call it my fact. Okay? What's the syntax look like?
Junction. Function.
Junction? Did somebody say junction?
Oh, function. That's where I'm at right now.
That's
I'm
awesome.
trying not to overlap.
You guys remember that program, Conjunction Junction?
Yeah. Oh, yeah, that was great.
That's a throwback. So what do I put here, and what do I put here?
Return value.
Yeah, so this is my return value, right? So what do we want to return? Let's just call it result.
Yeah.
And this is an argument or parameter. Those are the terms you can use for this. We'll do n. Yeah? We okay with that? All right, great. So let's build the result. It's a single line. What does that one line look like inside of this code that does my recursion?
Something my fact.
Yeah, okay, great. So we are going to call my fact from inside of my fact. And if I look at that equation as my sort of guiding principle, what parameter am I going to feed into my fact?
N-1.
N-1. So in my recursive call to my fact, in my next instance of my fact, I want it to work on N-1. That's how I progress closer and closer through the whole solution. Yeah? All right, good. Not quite done. We want to do some math here, right? If we want to replicate this guy.
So L equals N times my fact. N-1.
Well, when I make a call to my fact,
Yeah.
when my fact runs and is complete, in my equation, it will be replaced by the value of result.
Okay.
Right? So that result I want to then manipulate in this same exact way.
N-2 in there somewhere?
No, there isn't. This is the confusing part of recursion. Yeah. It's okay. N times. Yeah. So this corresponds to this. This is my fact, right? So I need to take the result of, like, when my fact is done, and that function, that instance, that execution of that instance is done, it kicks back a result. That result replaces this in a mathematical equation, or an assignment equation of it in MATLAB. So I'm going to multiply it by n. That's what I want to do. This is the local n of this function, multiplied by the creation of a new recursive instance of my fact that is going to work on N-1. Okay, and then where do I want to put that? In the result. Yeah. Okay. Let's keep it simple here. What's so funny? You guys are all laughing at me. I'm funny looking. That's what everybody used to say. All right. At a very basic level, this is not complete, but at a very basic level, this gets us started. Yeah. So let's kind of pretend. Can we pretend?
Yes.
I'm going to try to pretend I'm a computer and run through this. It's the only way to make any heads or tails of it. Okay. So I'm going to use boxes to kind of describe the instances or the console or etc. So here, I'm the console. Okay. You guys know what I'm talking about when I say console, right? That's or your terminal. There's a lot of different words for it, but it's that terminal, console, whatever. Command prompt. Yeah, exactly. Here, I'm just chilling, I'm waiting, right? And what do? I make my first call to my fact. So let's do that. My fact, let's do 4, okay? So that is going to spawn an instance of this function. I'm going to call it instance 1. We know it's my fact. I don't need to write that in. What is the value of n inside of this? 4, correct. Okay.
Why'd you put the 2 7s? Is that what it is?
I'm sorry.
Arrow.
There was supposed to be my command prompt. I'll take that out of there. I'm sorry. Damn. Okay. And my equation says result R equals n 4 times, and I'm going to put a big box here to represent another call to my fact. This is instance 2. What is the n value in here? 3. That's super hot.
I think you're just nervous.
What's that?
I think you're just nervous.
Because we're all laughing at it.
I know.
It looks silly.
Yeah, it says for sure. How long you had that?
Actually has a year on it, I believe. 1987.
No, it came out in 94, but I'm wondering if you got it in 94.
No, 97.
Okay. That's cool.
Sure.
That's what I'm here for the seat.
You have R
Yeah,
equals?
I am that old. Just kidding. Sorry.
You have R equals?
That's I replaced it. Sorry, just because I'm in a box and shorthand. Let's clarify that. Okay. Let's keep it consistent on both. Oops, this one I won't play. All right, so what's n in this? 3. I'm going to say R equals 3 times some empty box. Okay, that empty box is now another call to my fact. This is my third instance of it. Remember, and these are all isolated. They don't share variables or anything. The only thing they do share is the argument that's given to them and the variable that's passed back, the result that's passed back. Yeah? Everyone sees what's going to happen here, right?
Yeah.
No? Maybe? Sort of? Maybe. Okay, what's n here? R is going to equal 2 times a box. Instance 4. N is equal to what inside of instance 4?
1.
1. R equals 1 times a box. It's going to spawn another instance. This is instance 5. What's n equal in 5?
0.
0. R equals 1 times a box. That's going to call another instance.
-1.
Should I keep going, guys? What do you guys think?
I think we've exceeded our limit.
Oh, yeah, yeah. What did we do? We went past 1, right? The definition for factorial stops at 1, right? And you also know that 1 factorial is defined as 1, right? So this is to just show you that this is the core of recursion here. But if I don't create a stopping condition, which is one of the requirements for recursion to work, if I do not create a stopping condition, it will go on. That will go on forever and ever. It'll be like negative infinity and the computer malfunction. Okay? So when did we want this to stop?
At 1.
At instance 4, right? How do you think, using some stuff we've already known, how could we change this script to have it stop?
If n is I would not execute that line. I would say if n is greater than 1.
Hold on to your idea.
Yeah, yeah.
Who said wow? Okay, how would we do with the wow?
Well, n greater than or equal to 1.
Greater than or equal to 1? Equal to?
Yeah, so we wanted to stop at 1.
Yeah.
So greater than 0. I mean, we could also do greater than 0, right?
Okay, let's see. Let's see what this looks like. Yeah. So is this kind of what you're thinking? Yeah. Well, n is greater than or equal to 1. Do this. Yeah. Okay. Okay. So let's go over here. This instance, we're going to get. Are we going to stop here or make an additional call?
We're going to keep going.
Keep going. So we go to this one, right? And then here we're going to stop, right?
Right.
Okay. Okay. Then what's going to happen?
You guys send back 0.
Well, if I don't do this, all right, so let's stop for a second, right? This is taking us in a very nefarious path. Nefarious. This is taking us in a very nefarious way. Okay. I want to show why this actually creates a really interesting, different problem. I'm trying to think about how to do it here. Okay, this is how we do it. Let's forget about the ending condition. Okay, just for a moment. Let's think about this condition. Okay, let's assume this is all collapsed back up, and I'm returning a value. Okay. Upon return of that value, what's going to happen here? It's going to do this again. So in other words, after it's gone all the way out and back in and collapsed, it's going to spawn a whole new series. It's like recursive in a way. It's looping recursive is what it is. It's going to spawn a new instance of this, and it's going to do that n times effectively. Yeah. And so it may feel intuitive here to try using the while because we are looping, but the recursion itself is taking care of that while in the loop. The call to yourself is what's doing the looping for you. Yeah? So this is actually, I thought our problem was mostly at the end here, but actually the problem is even earlier.
But also at the end, like we would never enter the while loop. Therefore, we'd never assign an R.
You could figure out another way to do it,
Yeah.
but But I think the bigger problem is that when this myFact call comes back, you're going to do this again, and again, and again. And you really want, the recursion is, the looping is happening because you're making a new call, a new call, a new call by successive changes of the parameter to myFact. Yeah? Okay, so let's, how might we accomplish what you're trying to accomplish? How might we accomplish that maybe in a slightly simpler way without introducing it? Do if. Let's just do a conditional. Yeah? So what should we check for?
N is greater than 1.
So say if n is greater than 1, do this. Else,
Finish. And return. Right.
what should we return?
R. R equals N. Or R equals 1. No, R.
Yeah, I mean, r equals 1 may be a little safer, but yeah. Remember 1 factorial. The assumption is that once we get down to here, we're in a case where n equals 1. 1 factorial equals 1, right? This is definitely not the most intuitive thing in the world, so don't worry too much. Let's walk through it, okay? N is greater than 1? No. Right? So this next instance doesn't even happen. Okay? Does everyone agree with that? So here, what do I say? R equals 1. Okay? Good. So let's fill that in. Okay? R equals 1. This instance 4 finishes, completes. What happens to that R equals 1? Where's it going?
You return it to instance 3.
Exactly. This R equals 1
Doesn't look off.
is the result of this call to myFact, so it goes here. Okay? Then what happens? I can do this math now, right? Because this call is done, comes back.
R equals 2 times 1.
2 times 1.
Which returns to instance 2 into the box.
Okay, so I'm just going to say this goes up there. Then once this returns, this is all gone. Yeah? 3 times 2? That's the new value of R. That's the value of R in this instance. It's this work, the what work of this function is done. It comes back up here. What do we get? Same thing happens here. 6 times 4. Its work is done, and it gets returned to the console.
And that all happens in the span of a few milliseconds.
Yeah. So one thing to know about when you do this sort of call to a function from inside of a script or inside of a function, when you call myFact, this is true in MATLAB 1. It may not be true in other one. When you call myFact, this script that's doing the calling actually stops. MyFact gets called. It does whatever it needs to do. If it's lost in its while loop, for example, for 2 days, this function is just going to sit here and wait for this myFact to finish taking its 2 days. And after 2 days, hopefully a result comes out of it, and it gets plugged into here, and then this function continues executing. So the way to think about this function call is it's a pause in the execution of the calling script. During that pause, whatever you've called is executed. Okay? So when we're down here at instance 4, instance 3, 2, and 1 exist. They're all in memory somewhere, and they're all just waiting. When instance 4 finishes and has a result, instance 3 starts back up. It finishes up, has a result, instance 2 starts right back up. As a result, instance 1 starts back up. As a result, gives it back to you in the console, and the console becomes yours.
So is the console going to say function R equals whatever factorial?
This will be inside of your M file. This is as if you're building a function. And the console, to run it, you just call myFact. Should we try it in MATLAB?
Mm-hmm.
Yeah? Or should we talk about it symbolically more? Are you sure it's not hot? Guys are all dozing off. It's getting rough, huh? It's always getting rough.
Yeah. We got.
Yeah, go ahead, please ask it.
So besides these, factorials here and whatnot, what are the practical applications of some of these recursions?
So like I said earlier, when you have big data sets and you say you want to sort a big data set, recursion can do much faster sorts than other methods. If you have like the Google search engines, right? All that stuff is stored in like binary trees. To do searches in binary trees, recursion can be very fast. Those are some applications where recursion can be used. I can try to find some more examples in time permits. Let's see. Okay, so how do I make a function file? Oops, I didn't switch the. Yeah. That would have been bad. How do I make a function file?
Create a file with the same name.
The file name has to have exactly the same name as my function. It's called myfact.m. What is the other rule about functions? First line must be function declaration, right? Keyword function.
Well, what if you add some script above the function? Is that gonna?
Doesn't work. I mean, there is this sub-function thing, but we didn't talk about it.
Okay.
Yeah, it gets complicated. Function definition, function should be the first line.
You can also put comments.
After the function line, yeah.
You can put them above it.
It lets you do that.
And they go into the help function.
This is why like hardcore programmers get frustrated with MATLAB. It's like the rules are soft. That's good to know. Thanks. So it concatenates the help above and below. Fair enough. So what do we put first?
Oh, our
Yeah.
output.
R equals, and then it has to be, the keyword has to be exactly, the function name has to be your file name, right? MyFact. What are we going to put in here as the argument? And. All right, awesome. You guys remember what my code looks like? If. What am I checking for? What's the conditional that makes me want to keep going or stop? If n greater than 1, okay.
R
In time.
n times
All
n minus 1.
N minus 1.
Oh, minus 1. Okay, good. Good catch. Then?
L. R.
Done. That's it. Right? This is the same thing we had up there, right? Yeah. So let's do some display stuff to help us out, okay?
Do you have the right to turn on?
I don't remember. Do you?
I don't think you do.
All right, you got to
Just
worry about it.
once R has a value, it's automatically.
All right, thanks. Okay. So what I'm asking here is, I'm asking each of these instances as it executes through here. When it first gets called, it's going to say n equals. Okay? And when it's done, it's going to say r equals. So if I was to ask you this kind of question, it's kind of a really think about it carefully question. What do you think the output on the screen will look like?
Gonna do every value of n.
What do you think we're going to see first? Let's do the example with 3. Let's say I call my fact. And what I'm really trying to get you to think through is really how MATLAB's going to execute. Okay, let's say I do my fact 3. What's the first display you're going to see on the screen?
3.
N equals 3, right? What's the second display you're going to see on the screen? N equals 2, right? Because what's going to happen is the code is going to get to this spot. It's going to call a new instance of my fact. It's going to pause. The next thing that you're going to see is the second instance of my fact printing out n equals some number, right? And so you're going to see n equals 2. Then you're going to see n equals 1. Will we see n equals 0? No. What will we see after n equals 1?
R equals 1.
R equals 1, because that's that last instance of my fact. It'll finish. R equals 1 will come on the screen. What will happen after that?
R equals 2.
R equals 2. What happens after that? R equals 6. Cool. Okay, you guys did a very good job for predicting. So let's run it. Try it. Oops, I should have suppressed some of that, but hold on. Ooh. Is that what you guys told me? Awesome. How do we feel about recursion?
Sweet.
If I asked you to do it for Fibonacci sequence, Fibonacci series,
No problem.
Might be a little tough.
it's very similar to this. It's not that different.
Okay.
It's not that different. Cool.
I have a question.
Yeah.
So when we use a function like the function size, and you say, like values or dimensions equal size, and then you put your matrix in, it returns to one single variable, a vector with 2 values. But when we write functions that return more than one value, we have to use a specific syntax, which is like the squares with multiple variable names in it to be assigned. And I was wondering what the syntax would be to make it so that you could assign multiple return variables or values to just one variable, and it would be a vector.
I think the way to accomplish that is inside of your function, create the vector and return only the vector.
Okay.
We should test it. I'm pretty sure that's how you would do it.
That makes sense.
Yeah, I think that's right.
So let's say that size is doing that, and you return size, which is a 2-dimensional vector. That syntax where you do like the square brackets with the 2 different new variable names, that will naturally break a given vector apart, like into 2 different.
Well, I think so. I'm pretty sure that's like part of the, I think called slicing and dicing.
Okay.
Not dicing, it's called slicing.
But
But yeah, so
that makes sense because it's like you're concatenating, or you're deconcatenating something,
Yeah.
right?
I mean, in a way, what you're asking is what happens if we do this, right?
Yeah.
Like,
You needed a vector. You had a matrix.
yeah, I thought it might be able to work. Okay.
Yeah. That's weird. Yeah, see, so and maybe it's not actually doing that.
Okay, so this is getting a little tricky. Like it could be, like you can build functions to be context sensitive. Depending on how they're called, you can actually behave differently.
Okay.
That
Yeah, I was
may
just
be what's
curious
happening with size, but I'm not sure. I'm actually really curious to figure that out too.
We can
So
work on it.
maybe afterwards, like yeah, let's do it. Okay, cool. That's good. I just want to be explicit about some rules for recursion. Put them up on the marker board. Okay. So rules for recursion. For one thing, the function is going to call itself, right? You must have a terminating condition. There must be something in your function that stops it from existing. If you don't do that, you're going to be in a world of hurt. Okay, and then last, the successive calls, the successive parameters for the new calls must move towards the terminating condition. Okay, so what that means is if I accidentally wrote this function like that, even though I have a terminating condition, I will never achieve it because this parameter is not moving anywhere, is not moving in the direction of my terminating condition. And so if I accidentally make that mistake, I may have a terminating condition here and go, why is this still not for me? It's because I'm not moving there. Cool? Let's take a break a little early. See 10 minutes, come back, okay?